Trusses are everywhere. They are used in bridges, antenna towers, cranes, even in parts of the International Space Station. And for good reason. They allow us to create strong structures while using materials in a very efficient and cost-effective way. So what exactly is a truss? It is essentially a rigid structure made up of a collection of straight members. But that's not a complete definition. There are two important assumptions we need to be able to make for a structure to be considered as a truss. First, we need to be able to assume that all of the joints in the structure can be represented by a pinned connection, meaning that members are free to rotate at the joints. The members of a truss are often rigidly connected using what is known as a gusset plate. But if the center lines of all the members at a joint intersect at the same point, like they do here, it's reasonable to assume that the joint behaves like a pinned connection. The second assumption we need to be able to make is that loads are only ever applied at the joints of the truss. We never have loads acting in the middle of a member, for example. Because all joints are pinned, the members cannot carry bending moments. They can only carry axial loads. This simplifies the analysis of a truss significantly. Each member has to be in equilibrium, so the forces acting at each end of a member must be equal and opposite. Each member is either in tension or in compression. These assumptions are what differentiate a truss from a frame. Unlike trusses, frames don't necessarily have pin joints, and so members can carry bending moments. A frame can also have loads applied directly to its members. The base shape of a truss is three members connected to form a triangle. If a load is applied, the angles of the triangle won't be able to change if the length of each of the members stays the same. This means that the triangle is a very stable shape which won't deform when loads are applied to it, and so it is a great base from which to build a larger structure. Joining four members together does not form a stable structure. The angles between members can change without any change in the length of the members, and so using a four-sided shape as the base for building a truss would be a terrible choice. An easy way to stabilize this configuration is to add a diagonal bracing member to split it into triangles. We can start with our triangle and build it out to form a structure. There are a lot of different ways to build a truss, but there are some particularly popular truss designs that you will see again and again, and so they are referred to by specific names. The one shown here is a Fink roof truss, but there are many more, as you can see here. Later on in this video, I'll cover how these different designs carry loads in different ways. The members of these trusses are all located in the same plane. These are called planar trusses, and we can analyze them as two-dimensional structures. Even seemingly three-dimensional structures can often be analyzed as planar trusses. Take a look at this bridge, for example. The loads are transmitted from the horizontal floor beams to the two vertical trusses on each side of the bridge. Each of these trusses only carries loads acting in its plane, and so we can analyze it as a two-dimensional structure. To be able to design or analyze a truss, we need to be able to determine the force in each of its members. This allows us to check that the member can carry the loads without failing, or gives us the information we need to select the best cross-section for each of the members, and the internal forces in the members of a truss by applying the equilibrium equations. The truss is said to be statically determinate. Real-life structures sometimes contain more members than are needed for the structure to be stable, as this makes them safer. This means we may not be able to apply the method of joints or the method of sections, because we have too many unknowns and not enough equilibrium equations, either to determine the reaction forces or to determine the internal forces within the truss. These trusses are said to be statically indeterminate and would need to be solved using other methods like the force method or the displacement method. Let's explore some of the differences between truss designs. Here we have three different bridge trusses: the Howe, Pratt, and Warren trusses. These trusses were all patented in the 1840s, at a time when new bridge designs were being developed to accommodate the expansion of the railroad industry. They were typically constructed from a combination of wood and iron. We can learn a lot about truss design by figuring out which members are in tension and which are in compression. Let's start with the Howe truss. We can see that its vertical members are in tension, and its diagonal members are in compression. Members in compression usually need to be thicker than members in tension to reduce the risk of buckling. This means that the Howe truss isn't very cost effective, since the diagonal members, which need to be thicker, are quite long. The Pratt truss addresses this issue. Its vertical members are mostly in compression, and its inner diagonal members are in tension. This is more cost effective than the Howe truss, since the longer diagonal members can be thinner. Longer members are also more susceptible to buckling under compressive loading than shorter ones. So it's a good idea for long members to be in tension. The design of the Warren truss was based on equilateral triangles. The fact that all of the members are the same length is an advantage for construction, and it uses less members overall than the Howe and Pratt trusses, so it is more efficient. The diagonal members alternate between tension and compression, so it does have some quite long members in compression. It can also be interesting to observe how the loading in members changes as a load moves across a bridge. In this simplified model of a load moving across the Pratt bridge, we can see that some members alternate between tension and compression, and so will need to be designed accordingly. The three-dimensional bridge we looked at earlier could be assessed as a collection of planar trusses, but this won't be possible for all structures, and sometimes a truss will need to be assessed in 3 dimensions. This type of truss is called a space truss. These can be analyzed in essentially the same way as planar trusses, using the method of joints and the method of sections. The only difference will be in the number of equilibrium equations.